Welcome back, physical science students, to our last video of the unit on chemical bonding. Today we're going to talk about inter versus intramolecular forces and bond properties. So the unit test for our second unit is going to be released on Thursday and then due on Sunday like normal. We'll also get our first round of notes for our next unit, which is states of matter. Again, remember there is only about a month left of school. That means 4 weeks until we are done with school. So make sure that you're staying on top of things and you're getting your assignments turned in, you're asking questions and that sort of thing, so that we can just kind of coast to the end of the year and get everything that we need to. So without further ado, let's get into our video on inter versus intramolecular forces. All right, so first let's talk about what we mean by intra versus inter. Okay, so intramolecular forces are the ones that we've already been talking about. Those are going to be within the molecule. That is your covalent bonding and your ionic bonding. Okay, so make sure that A is the difference between whether we're talking about the stuff inside or the stuff outside. Okay, so this is like when we share electrons in covalent bonding, or we give away electrons in ionic bonding. Okay, so remember that intramolecular forces are what we've already covered in this unit. Okay, covalent and ionic bonding are intramolecular forces. Intermolecular forces are between molecules, meaning that if I have a molecule of water here and a molecule of water here, there's some kind of force that attracts them, because obviously we don't have just one molecule of water sitting alone by itself. There's multiple things or multiple molecules of water, and they are attracted to each other to make water the way that it is. Okay, and so we're going to be talking about different types of intermolecular forces here throughout this video. Okay, these molecular forces also segue into our states of matter unit, because you need to break these forces in order to change the state. So for example, in order to change water from liquid into gas, you need to overcome these intermolecular forces that are connecting these molecules together. Okay, these are weaker than the intramolecular forces like covalent and ionic. They're a lot easier to break. It's very, very difficult to break a covalent or an ionic bond. Those take an incredible amount of energy, whereas intermolecular forces are weaker than them, and they can be broken with heat, through dissolving things. All kinds of things can break those intermolecular forces. Okay, so let's talk about the very first one, and it is dipole-dipole. Dipole-dipole forces are actually, we're going to have three that we talk about. They're the middle force that we're going to talk about. So we have one that's stronger, and then we have one that's weaker as well. So dipole-dipole forces act between two or more polar molecules. And so if you remember from previous videos or previous activities, polar molecules are only covalent bonds. Okay, so it has to be some kind of covalent bond. So down here, you'll notice that I have HCl, hydrochloric acid. And so basically what happens is that you get one side, because if you remember back to polar, one side becomes positively charged, one side becomes negatively charged. Well, if you have a whole bunch of molecules, then all of the positives and negatives are going to orient themselves and have slight attraction. Okay, so if you imagine molecules orient to maximize the plus minus and minimize plus plus and minus minus attractions. So chlorine here, I don't know if you guys can see my cursor or not, so I'm going to circle this. Okay, chlorine here is slightly negative charge. Okay, hydrogen has a slight positive charge. And so when I get a bunch of these atoms all around, okay, the positive hydrogens are going to be attracted to the other chlorines in this mixture. Okay, so if I have like a vial of hydrochloric acid, I'm not going to just have a couple molecules, there's going to be millions of molecules, and they're all going to have this attraction of slightly positive to negative attractions. And so those are what we call dipole-dipole forces. Notice again that I'm talking about between molecules. This is not inside molecules. This is one molecule to a different molecule. Okay, strength decreases as distance between the dipoles increase. So if you remember from previous science classes, when you heat things up, okay, the molecules tend to expand. And so the strength of those dipoles is decreased because the distance between them is increasing. Okay, and that's eventually how you get things to boil, is you break those dipole-dipole forces, and eventually the molecules are so far apart that they don't have as much of an attraction. All right, and the next one is hydrogen bonding. Now, the good thing about hydrogen bonding is it is actually a type of dipole-dipole, but it's kind of like a subset of them. So we have all of dipole-dipole forces, and then inside that we have specific hydrogen bonding. And it's a very, very strong type of dipole-dipole. So in our three, hydrogen bonding is the strongest, second is dipole-dipole, and we'll talk about the third one here in a second. But hydrogen bonding, large bond polarity and proximity of dipoles. So this is still the same plus minuses attracting to each other, kind of like that hydrochloric acid that we had with HCl. The hydrogen atom is tiny. It gains this positive charge, and so it is greatly attracted to the big negative charges that some of our elements have. And to remember whether it's ever hydrogen bonding versus just a regular dipole-dipole, if hydrogen is ever bound to nitrogen, oxygen, or fluorine, you're going to have some kind of hydrogen bonding. So for example, in water, H2O, that's hydrogen bonded to oxygen. So there's a very strong hydrogen bonding going on between the molecules in a tub of water or however much water. Okay, the attraction between the water molecules is hydrogen bonding, a very, very strong type of dipole-dipole bonding. Okay. Now, one way to remember this, and this is the way that chemists tend to remember when we have hydrogen bonding is FON. So whenever you have a hydrogen bonded to, again, fluorine, oxygen, or nitrogen, it's kind of just an easy saying to remember which ones are going to be hydrogen bonding. If hydrogen is bound to anything else, like in my previous one when I talked about HCl, that is dipole-dipole. It is only when I have HF or HO or HN. Okay, anytime you have those, it's going to be hydrogen bonding, and no other time is it going to be hydrogen bonding. It would be, if it's polar, it's going to be dipole-dipole. Okay, you can kind of see on this chart that this hydrogen bonding influences the physical properties. It causes boiling points to be really, really high. Okay, so you can see down here that I have H2O with a boiling point of 100 degrees Celsius. Hydrogen and fluorine bound together with HF, and that's up there as well. And then we have these ones down at the bottom that show that other things have really low boiling points. Okay, just trying to piggyback the intermolecular forces into the different physical properties of our compounds. All right, the last one, third and weakest of them all, is the London dispersion forces. Okay, and so these exist among noble gas atoms and nonpolar molecules. So if you have ionic bonds or nonpolar covalent bonds, this is the one that connects them together. Okay, importance increases as the size of the atom increases. So the bigger the atom, the bigger the London dispersion forces, and that's mostly just because they have bigger charges, bigger nucleuses or nuclei that have bigger attractions and that sort of thing. Okay, and so what happens here is that you have a momentary non-symmetrical electron distribution that creates a dipole-dipole situation. So as you have this atom, okay, electrons are going around the nucleus incredibly fast. Okay, and so when you have two of them, there's a momentary time where an electron is on the outside of one and it's temporarily so far away from this nucleus that it's actually attracted to the molecule next to its nucleus. And so we get this temporary attraction of a positive to a negative, and it creates this force that holds these electrons together. Now, this is momentary, this is very short-lived because the electrons move so fast, but it does create a force between molecules that keeps them together. Okay, so up here in the top right, you can kind of see that the green lines are the repulsive forces and the purple lines are the attractive forces. So the nuclei of two molecules that are next to each other are going to repel each other. Okay, whereas the electrons are going to be attracted to the nucleus and the electrons are going to be repulsive of each other. And so as these things are spinning around, you get these temporary attractions. Okay, this leads to interatomic attractions that is weak and short-lived, but for really big atoms, it can be very, very significant because big atoms can pull those electrons a lot towards their nucleus, creating a pretty big, strong force. Okay, noble gases have low freezing points. Atoms must really slow down in order for interactions to be strong enough to produce a solid. Which is why noble gases tend to be gases, because it's really difficult to get their molecules close enough together to actually create a solid or even a liquid. And that is what that last point is talking about. Okay, nonpolar molecules lack permanent dipole moment, use London dispersion forces to attract each other. Okay, so we don't get the dipole-dipole forces that we first talked about are only very, very momentary, and so they only use London dispersion forces to attract each other, meaning that there's not a whole lot of attraction going on constantly. It's very, very momentary, and then it changes, and then it's momentary again, but it does keep those molecules together. Okay, so moving on. So those were our three intermolecular forces that we're going to be talking about. So mostly what you need to look at, again, if you go back to our last video on identifying what kind of bonds each thing is, anytime you have an ionic bond, it's always, always, always going to be a London dispersion. Okay? If you have polar covalent, it's always going to be a dipole-dipole. And then if it's the special case where it's hydrogen and fluorine or oxygen or nitrogen, then it's going to be hydrogen bonding. If you have a non-polar covalent bond, it's going to be London dispersion as well. Okay, so it's very important that you're able to identify those bonds, because then you can identify their intermolecular forces. And then when you can identify their intermolecular forces, that allows you to understand the properties of the bonds, which is what we're going to talk about now. Okay, so things that we're looking for in the properties: solubility in water, its melting point, and its conductivity of heat, both heat and electricity. Okay, so those are the three that we're going to talk about, and the three you're going to have to know on the test. All right, so I put it all together in this nice little chart for you to write down and for you to know. So let's go through conductivity first. Okay, conductivity, so again, this is the ability to let heat or electricity run through them. Covalent bondings, low conductivity, poor heat and electricity conductors. Okay, so covalent things that are covalently bonded do not tend to have high conductivity. Ionic bonding, low conductivity as a solid, but when they are dissolved in water, they have high conductivity. And what you can think about with this one is, for example, let's say salt. Okay, salt is an ionic bond. If you just hook up something to a salt crystal, it's going to have really low conductivity. Okay, you're not going to be able to pass electricity through a salt crystal. But once it's dissolved in water, it's actually a really, really good conductor of electricity. Okay, so that's what it means there. Metallic, remember that metallic bonds are just metal bonded to other metal. And if you imagine anything made of metal conducts both heat and electricity. Okay, so all the wires that go through electric motors or whatever you can think of, very, very good at conducting electricity. Let's go to solubility in water. So this is the ability to dissolve in water. Covalent bonds do not dissolve in water. Now, the unfortunate thing about this online learning is we do a whole lab on this where I have you test all of these things. So I have some wax that is a covalent bond. I have salt, which is an ionic bond. I have different types of metals, and I have a bunch of other materials. And we actually test all these things. And unfortunately, we're not going to be able to do that, which is a bummer because it's one of my favorite labs. But solubility in water, for example, the covalent bond in wax, if you just drop dry wax into regular water, it does not dissolve. So that's why the covalent bond is not soluble in water. Ionic bonding is, okay, ionic, I always use salt as an example. That's definitely soluble in water. Salt dissolves in water, as most of you know. Metal, not soluble in water. Okay, if I just drop a piece of copper or steel or whatever into water, it's not going to dissolve. Lastly, we talk about melting points. So this is again going to be the point in time where you change from a solid to a liquid. Again, when we talk about states of matter and we talk about these phase changes, we'll talk more about melting point and how these forces attribute to those. But anyways, covalent bonding, if you think covalent bonding is like the wax that I was talking about, very, very low melting points. Very easy to melt wax. Okay, it does not take very much heat to melt wax. Okay, ionic bonding, highest melting point. If you just take a crystal of salt, it is incredibly difficult to make that go from a solid salt crystal to melting into a liquid. Incredibly difficult. Okay, and so I kind of have them ranked here. Covalent has the lowest melting point, ionic has the highest, and metallic is also up there for a pretty high melting point. If you think about the amount of energy or the amount of heat it takes to melt metal, okay, that is what goes into breaking those metallic bonds to create molten metal. Okay, and honestly, guys, that is all I have for you. Make sure that you finish the assignment for this week. Make sure that you're getting caught up on past assignments that you may have missed. Making sure that you're getting your quizzes in and all of that. And other than that, thanks for watching.